Good morning. All right, let's get started. Is there any questions? Any questions? Any questions? All right, so just in case you missed Tuesday's class, we did something very, very important. There are lots of resources, but go after it. It's not going to go away, and it's just so central. And today we're going to do the other one. So what we're doing today is also very, very important. So the story of our number system is basically we started with the natural numbers. And then we found that not every difference, not every quotient lands in this set. We fixed subtraction, we got the integers. We fixed division, we got the rational numbers. And the rational numbers is the only, is the first number set or number system that's closed under the basic 4 operations. There's a bit of glitch about division by 0 that actually cannot be fixed, but anything else you try, the sum of 2 rational numbers is rational, the difference, product, quotient, you can, it looks like we could have lived with it, but it still wasn't enough, right? So natural, integer, rational. And then we have seen that there are strange numbers that are not rationals. So add irrational numbers. And that's how we get the real numbers. So that exists. Well, maybe I should define it. So a number is rational if it can be written as a quotient of 2 integers. An irrational number cannot be written as a quotient of 2 integers. Irrational number, it's the same sentence with the word not strategically inserted there. It cannot be written as a quotient of 2 integers. Examples for irrational numbers. Well, we have seen pi and square root of 2. But there is more. Pretty much any number you put under the radical, unless it's something as nice as 9 or 25, then that square root is irrational. Square root of 3 is irrational, square root of 5, 6, 7, 8, 10. So there is no middle ground. It's either very nice or very bad. There's no, just a little bit bad. Now we also have looked at decimals. And we have the following facts. 1, terminating decimals represent rational numbers. And that was an easy fix. You just grow a 1 and a suitable 10 power multiplying upstairs and downstairs will do the job. And then we have also discovered that non-terminating repeating decimals also represent rational numbers. Okay. So there is this idea, concept of exact values. Exact value means it's not approximation. It's exactly that. It's not really, really, really close. It's that. And in algebra, we're gonna carry things in their exact value form. And if there is an approximation using the calculator, it's on the last line. So inside a computation, you're gonna carry exact values. That is pretty much all over the place, not just in algebra, but even in other branches of mathematics. So how can we write square root of 2, the exact value? Oh, before we do that, let me define square root of 2, just in case. Square root of 2 is a positive number that when squared, we get 2. It squares to 2. So this is, to me, this is true by definition. Square root of 2 is the number, the positive one that is, that if we square it, we get 2. That's the definition. Plus, it's not the negative one, right? There is a negative one too, the opposite of square root of 2. So that's the definition. And so now the question is, how can we write square root of 2 without losing precision? So we want to keep the exact value. Okay, so could we write it as a fraction of integers? So the question is, could we perhaps write square root of 2 as a fraction of 2 integers? I await your answer. Could we write square root of 2, the exact value, as a fraction of integers?
No.
Feel free. Oh, yes. Oh, thank you. Thank you for talking to me. Why not, you think? You're right.
Because it's an irrational number.
Exactly. That we can't do that. It's the definition of rational numbers that we cannot. And we did prove it, right? We did prove. We assumed that there are 2 integers A and B, and we got into all kinds of crazy things from that. So no, because square root of 2 is irrational. That's kind of the point. Oh, thank you for answering. Okay, so let's try decimals. Imagine that we want to write square root of 2 without losing precision as a decimal. Square root of 2 as a decimal. Can it terminate? Can it be a terminating decimal? No, because that too would make the poor thing rational, right? Terminating decimals always represent rational number. So no, no, that would make square root of 2 rational, which it isn't. What about, so far, no fraction, well, not a fraction of integers, and then the decimal does not terminate, so it goes on forever. Could it repeat? No, because that too would make it rational. The chop game is all about, if you have a repeating decimal, that represents a rational number. So what is left for poor old radical 2 as a decimal? What is left for it? What must be the decimal presentation of square root of 2 look like?
Are you asking what the decimal is of the square root of 2?
No, not specifically what it is, but describe it. It can. What does a decimal look like if it cannot terminate and it cannot repeat? What does that look like? I don't know. It goes on forever without repeating pattern. It never stops, and it can have patterns as long as it doesn't have that repeating block pattern. Now, with our finite life, finite paper, and finite carbon resources, we could spend our entire life writing down the digits of square root of 2, and we would still not capture the exact value because we don't live forever. Square root of 2 as a decimal does go on forever. You see the problem with the decimal? It's just terrible. Because anything nice we proved is rational. So what's left for irrational numbers is pretty bad. So the decimal presentation of irrational numbers, including square root of 2, is non-terminating, non-repeating. In fact, this is one way to generate irrational numbers. So if you here is a famous irrational number that we can generate just by generating a decimal that we make sure never stops and never repeats. So here it is, 0.1. Well, that's rational. We can never stop. And then I'm going to put another one down, but first a 0. And then I'm going to put another one down, but just to make sure it's not going to repeat, I'm going to put 2 zeros there. And then 3 zeros there. And then 4, and so on. That's a famous irrational number that is generated in such a way. But if we keep all the zeros, we can change these decimals in any way we like them. In fact, you will see that if you write an infinitely long decimal, where you never stop and you never repeat, there are so many options. Once you start repeating, you have no choices just to repeat the same thing. So that's why I just kind of want you to have a feel for how many irrational numbers are there, how many different ways can we write an infinitely long sequence of digits where the sequence is infinite. So every once in a while there is a non-zero and there is no infinite repeating. You can repeat 100 times and then something else comes. So there is actually just so much more irrational numbers than rationals. But here is what we stuck with. The exact value of square root of 2 is going to represent it like this, square root of 2. There is nothing else that we can do without losing precision. And the idea is, if you present your answer like square root of 2, then the reader can get their calculator and get the precision that they need. But if you punch in square root of 2 into your calculator, and you write down 1.4, well, the reader will have no idea where this approximation came from. For all we know, it could be 14 over 10, right? So it's not just you lose precision, you lose information. If you just give the reader square root of 2, they will know what to do to get the precision that they need. So here is the bad news. Every irrational number has to be, the exact value is kind of tricky. For example, for 3.14, blah, 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 there is a Greek letter pi. Because anything else we try would be, at best, approximation. By the way, some kids from Africa usually think that pi is 22 over 7, which it isn't, because pi is irrational, and 22 over 7 are integer over integer. What 22 over 7 is a surprisingly good approximation, considering how small 22 and 7 are. It's just a surprisingly good approximation. So, yeah, every once in a while, I have to talk people out of thinking that pi is 22 over 7. No, it's not. It's just close enough. So here is the bad news. Now we have to learn how to, now we have a new guest in our algebra, and we have to learn how to deal with it. We first started with the numbers, then came the letters, and now come the hideous numbers. And then in physics, after that come the units. It's like one more guest. So we have to learn how to deal with radical expressions. The good news is it's not that difficult, and it's kind of fun. Is there any questions before we get into it? Okay. All right. So let me just get out of the way that square root of a plus square root of b is not square root of a plus b. So remember, radicals are multiplicative creatures. They will behave well with respect to multiplication, division, but not addition, subtraction. Just try a 16, b 9. A is 16, b is 9. The left-hand side is square root of 16 plus square root of 9, which is 4 plus 3, which is 7. Meanwhile, square root of 16 plus 9 is square root of 25, which is 5, not 7. Same with minus. However, multiplication, yeah, that's cool. Square root of a times square root of b is square root of ab. Well, I have to be a little bit more careful and say something like when both sides exist. we talked about domains before, right? So there is a domain issue. If A and B are separately negative, then you multiply them together. It's positive. Positive numbers have square roots. But if A and B are negative, this side doesn't exist. Square root of a negative is undefined, and undefined times undefined is undefined, right? So when both sides exist, then they are equal to each other. This one has a more generous domain. This allows A to be negative as long as B is negative as well. Okay, any questions so far? So this is quite a useful rule, and this is the first one that I introduced because I think that square root of 5 squared is 5 because of the definition. That's the definition of square root of 5. On the other hand, here's what I see on quizzes, exams, and I cannot really talk people out of it, is that square root of 5 squared is square root of 5 times square root of 5 is square root of 5 times 5 is square root of 25 is 5. Not incorrect. I just think it's way too much work when, I think it's true by definition. We don't need to bring it. But you see, this rule is being applied when we went from here to here. So whenever I introduce the definition, I always feel like I should show you that too, in case you want to stick with this. There's nothing wrong with that. No, there's nothing wrong with it. Okay. All right. So yeah, let's just have a quick list here. Square root of 0 is 0, no problem. Square root of 1 is 1. Because 0 squared is 0 and 1 squared is 1, square root of 2 is irrational. And square root of 3 is irrational. And square root of 4 is 2. So basically, if you take an integer, the square root of it is either irrational or integer. Nothing will be just a fraction. That's what I refer to as no middle ground. Square root of 5 is irrational again. And square root of 6 is irrational. And so is square root of 7. The square root of 6 is a good example because this number doesn't have to be a prime number so that it doesn't work. As long as it's not a square, and all bytes are irrational. Square root of 8 is irrational. Square root of 9 is nice again. Square root of 10 is irrational. And so on. Let's do a few more. I want to reach at least square root of 12. Square root of 11 is irrational. And square root of 12 is irrational. So it's square root of 13, 14, and 15, and then square root of 16 is nice again. By the way, I just want to point out that you have a really smart calculator. In my time, when I took, say, 15, and I took its square root, it gave me the same decimal. But it remembered the decimal. Therefore, if the calculator remembers the decimal, that's not the irrational number itself, a finite decimal, I mean. So when I took square root of 15 in my calculator and squared it back, I never got 15. I got something like 14.999983. But it was still obviously close enough for me to know. But you guys have a really smart calculator. Somehow it's programmed to do symbolic computation. Way back in another millennium, that wasn't how my calculator behaved. And so these are good things to check for. All right, any questions so far? Okay, so let me just say that square root of 2 and square root of 3 and square root of 5 are like X, Y, and Z. They are unlike terms to the numbers, and they're unlike terms to each other. They're terrible. So not only there is going to be one group of nasty numbers, there is going to be more than one group. So you're going to see similar expressions. That's intentional. So simplify. Two x minus 3, 3x plus 5x minus 4 plus x, 2 square root of 5 minus 3, 3 square root of 2 plus 5 square root of 2 minus 4 plus square root of 2. All right. I just want you to understand the analogy, like it's pretty smooth. So how can we simplify 2x minus 3? You're right, we can't. Similarly, 2 times square root of 5 minus 3 cannot be simplified any further. This is what final answers will look like. Now, what about here? How can we simplify this expression? 3x plus 5x minus 4 plus x. Chop, chop.
Combine like terms.
Exactly. We get 9x minus 4. Very good. Apply the same idea. Square root of 2 is a whole lot like x. It's nasty and unlike term to the numbers. So you just need to combine it like usual. So what do you think we'll get here?
9 square root 2 minus 4.
Exactly. That's what I meant, that they are like x. So we have 9 square root of 2 minus 4. Yeah. Sometimes a student of mine asked, when we had something like minus 3 plus square root of 2. So my student asked, do I always have to put the nice number up front and then the radical? Is there a sort of a standard form? And my answer to that is no. In fact, some people will swap it just to save the 1 plus sign that they don't have to write. You see that this is one less character to write? So some people in mathematics are just that lazy. So it doesn't matter in what order, as long as it's simplified. Just like with minus 4 plus 9x is correct. It's a little weird, but there's nothing wrong with that. And then my other comment is that I very often see a really cute mistake, and I just want to preemptively make sure you don't do that. Now, how would you simplify 3x minus x? Oh, come on. I'm gonna start yelling at, yeah, it's 2x. And that's pretty obvious. And yet I see something, a silly little mistake often that people sort of cancel this out. And then I don't know what they write, 3 or 3 minus 1, or just, it's just goofy. This is as silly as canceling out x there, but for some reason I see it a lot. So don't do that. Instead, 3 root 2 minus 1 root 2 is 2 of them. 2 square root of 2. Okay. All right. And then if you have something like 3x plus 4y minus 1 minus x plus y plus 6, how would you simplify that? Oh, come on. This is going to be like dentistry. I would have to pull every answer out of you. Yes. So 2x minus 3x minus x, that's 2x. 4y plus y is plus 5y, and minus 1 plus 6 is plus 5. And it cannot be simplified any further. So guess what? If I ask you 3 root 5 plus 4 root 3 minus 1 minus square root of 5 plus root 3 minus 6, and yes, I intentionally used pretty much the same expression. How can we simplify that? So instead of 2x minus x, instead of 3x minus x, it's now 3 root 5 minus root 5, but the concept is the same. We're gonna get 2 square root of 5. Instead of 4y plus y, it's now 4 root 3 plus 1 more root 3. And I messed up something, yeah, same. So they're pretty much like x when it comes to adding and subtracting them. Radicals are like terms with just themselves, not with the numbers and not with other radicals. So it's pretty bad. Okay, so next up, what I want you to do is a pretty useful little technique that will come up, and that is approximating a radical by placing them between two consecutive integers. For example, square root of 20. Now, square root of 20 should be between two integers. Think of a number that squares to something less than 20. Wait, no. Find a square number just before 20 and just after 20. What are the two square numbers around 20? 20 is not a square number, but it's between two square numbers. What are those two square numbers? Thank you. You should know the square numbers until, I don't know, 15 would be nice. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 196, 225. Just, I don't know, it will make your life easier. So indeed, 20 is between these two. And because 20 is between 16 and in between 25, that means that this number is between 4 and 5. Does that make sense? Because 4 squares to 16, that's not enough. And 5 squares to 25, that's too much. Of course, you can always enter, but this is still important. So square root of 20, and we already know it should be 4 and change. 4.47. Okay. Can you? Okay, let's do another one. How about square root of 50? Place it between two consecutive numbers. Place square root of 50 between two consecutive integers.
$49 and $64.
Yeah, and it's pretty close to 49. So this is going to be probably closer to 7 than it is to 8, right? 50 is between 49 and 64, which is why this number is somewhere between 7 and 8. And I suspect it's going to be closer to 7 than to 8 square, because it's almost square root of 50. All right. Is there any questions about this? By the way, you can do that with third roots as well. You just find 2, 3 powers, one before, one after. But let's just stick with square roots for today. Okay. No questions so far? So far, so good? Okay. So then I'm going to show you something crazy. If I find it. When I try to make it up, I mess up. So I just put it in my smart book. Oh yeah. Square root of 12 plus square root of 27 equals to square root of 75. That looks wacky, doesn't it? I'll try one more. There it is. No, it's not there. Okay. Okay. I'm sorry. All right, I'll get a little. So square root of 8 plus square root of 18 equals to no, I'm sorry. See, that's right. Square root of 2 plus square root of 8 is square root of 18. That looks pretty wacky too, doesn't it? Okay, so we can actually sniff this problem around with the calculator. Check this out. I'm gonna add square root of 12 and square root of 27, and then I'm gonna square the result, and it's gonna say 75, right? So square root of 12 plus square root of 27 is a number between 8 and 9. 8 squares to 64, 9 squares to 81. So far it's possible. And I'm going to square it, and there it is. How whacked out is that? I'll do the same with the second one. Square root of 2 plus square root of 8 equals to a number that if I square, I get 18. What do you think? Pretty crazy, isn't it? It's not that crazy, but it's kind of fun. So, but it's very important that you understand it's not as simple as that. In fact, it's this wacky like this. Okay. So, you know, you wouldn't believe it, but there was like 2 generations ago, there weren't any calculators, let alone computers. And if calculators were available, they weren't in the education. People use logarithmic slides and table of books of tables of values for radicals and stuff, and all kinds of computational trickery to get by. So the calculator is kind of fresh. So we still have habits today in our curriculum that are basically there because people used to not use calculators. And now it's a little bit strange that it's there, but still. So now let's recall that square root of 18. Oh, sorry. Let's recall that square root of A times square root of B, when both sides exist, is the same as square root of A times B. And now here comes the magic. So I'm gonna look at this. Square root of 2 plus square root of 8 equals square root of 18. So square root of 8 is square root of, and now I'm gonna express 8 as a product where the first piece is gonna be a square. How about 4 times 2? And then now I'm gonna apply this identity, but in this way, and say, well, that's the same as square root of 4 times square root of 2. And I I intentionally put the first number to be a square because this is sort of the recyclable part. This is the part that's salvageable. Square root of 4 is 2. So now if we go back to square root of 2 plus square root of 8, we can rewrite square root of 8 as 2 times square root of 2, right? So it turns out that square root of 8 is not unlike term with square root of 2. Now what is this? How can we simplify this?
Would it
Three.
be
Exactly. It's 3 square root of 2. Thank you. And then square root of 18, the other side. 9 is a big square in 18, multiplication-wise. So we separate the two because the first part is the recyclable, the salvageable part. So square root of 18 is the same as 3 root 2. So the fact that square root of 2 plus square root of 8 is square root of 18 is not as worked out if you think about it as square root of 2 plus 2 square root of 2 is really 3 square root of 2. Then it doesn't look all that crazy, right? But that's what's going on. There is another way to see this. So square root of 18 equals 3 root 2. Another way to see this. What do we get if we square both sides? If we square square root of 18, by definition, we get 18. And if we square 3 root 2, then, you know, there is this rule of exponents that we can square a product factor by factor, right? So that's 3 squared times square root of 2 squared, which is 9 times 2, which is 18. And probably the calculator will do this faster. So we can say, all right. So there is a new, rich and playful, but new algebra going on here. So 3 times square root of 2 is not square root of 6. It's square root of 18. I'll square it. There it is, right? It's a very common and pretty serious error to think something like square root of 40 is 4 square root of 10. That is not true. What is square root of 40? Now, if you express the number under the radical as a product, where the first number is the biggest square you can find, then the second number is, it's like fat-free, but with squares, it's square-free. So square root of 40 is not 4 times root 10, it's root 4 times root 10, right? Okay. Any questions so far? Okay, so this is when I'm very much in disagreement with the official status quo. Officially, square root of 40, bad, unsimplified, and 2 square root of 2, good, simplified. So theoretically, you will be marked wrong if you turn in your final answer as square root of 40. I think that's stupid. I can't find other word to express how silly that is. I think half the time this is better. I mean, if you have to square, what would you prefer to square? Square root of 40 or 2 times root 10? I think this is simpler to square. Just remove the square root. So as a final answer, they're perfectly acceptable, both of them. So you don't have to simplify for me, but And the interesting conversation, which is completely missed out when people say, oh, this is bad, this is good, this is always no, this is always yes, is because really inside a computation, half the time this will serve you better, half the time that will serve you better. But it's going to be a little bit tricky because will I be marked wrong if my final answer is square root of 40? No, because I don't see 2 times root 10 as a significantly better thing than this. But what about something like square root of 40 plus square root of 10? Now, even I say that, no, that's not simplified, because if you were to drag out the squares from root 40, you would get 2 root 10, and 2 root 10 plus 1 root 10 is much more complicated than just 3 root 10, right? So yes, should be 2 root 10 plus root 10 equals 3 root 10, right? You see the point here, right? This is much more complicated than this. So in a way, if your final answer is a radical alone, well, make sure it's not like 49 under the radical, because that should be simplified to 7. But if it's 40 under the radical, I couldn't care less. But if it's square root of 40 plus something that turns out to be on the final analysis related to it, so you can combine like terms, then this is not simplified, not even for me. And then there is the gray area. What if we have something like 5 times square root of 40? Let me make a different. How about 3 times square root of 40? So then the thing is that one advantage of square root of 40 over 2 root 10, that there is nothing multiplying it. Now there is a number multiplying it. Might as well drag out what we can, drag out that root 4, which is gonna, because this one is simpler, because the numbers are smaller, right? But I would not mark you correct, but that's a sort of a gray area. It might be in your own interest to start dragging things out if you're already inside a product. Does that make sense? So always fine, never fine. I will accept it, but it's probably best for you if you work it. Okay. Any questions? So if I go back to our list where I promised that everybody is on like terms, it's not as simple. Square root of 8 will talk with square root of 2. Right, these two are actually like terms. And the reason I wanted to go until square root of 12, because 4 times 3 is 12, so this is 2 root 3. Under the radical, you have 4 times 3, root 4 is 2. So square root of 3 and square root of 12 are related to each other. So that's the full story. Okay, any questions? All right, let's look at this other vectored out statement. Root 12 plus root 27 equals root 75. Root 12 plus root 27. Let's simplify this. How can we simplify square root of 12?
Three times 4.
Exactly, but I'm going to put 4 up, 4 first, because that's the salvageable part. Now, if the problem says simplify, that's what I call student logic. If you're given a problem on an exam for 5 points and they say simplify, it probably can be simplified, right? Teachers will not make you do nothing for 5 points. And so this problem only works if the unsolvageable part is the same. So you already know to divide by 3. This problem only works if the second piece is the same. Otherwise, they will not be like terms. So once you sort of tackle the first part, the rest should be easier. So root 12 is 2 root 3. And root 27 is 3 root 3. And that's together is 5 root 3. Whenever someone says simplify, this is what they want as answer. Because officially all the squares have to be dragged out, right? But there is virtue in shoving 5 under the radical. So it's not just you can drag things out, you can shove things back under the radical. If I want this to go in, let's just write 5 as a square root of something. 5 is square root of what? 5 is the square root of?
25.
Exactly. So we rewrite 5 as square root of 25. And now we apply the same little identity that root A times root B is root AB, and that is your 75. No one will want you to come up with this, but I think this is fun, that these two would be, now you see why. But it's kind of crazy. But there is virtue in that one. Let me show you an example why sometimes you actually wanna shove things under the radical. Suppose I ask you to approximate four times root 5. Okay, now, so option 1, place it between two consecutive numbers. Option 1, well, we can say square root of 5 is clearly something between 2 and 3, right? Because 2 squares to 4, not enough, and 3 squares to 9, too much. And then we can multiply all 3 sides by 4, and then we get 4 root 5 is between 4 times 3, which is 12, and 4 times 2, which is 8. That's not bad, but we get a much better approximation if we just jam that 4 back under the radical. Rewrite 4 first as a square root of something. Whose square root is 4? Hey, 4 is square root of what? (16). So we can rewrite 4 as square root of 16. And then we have this lovely identity that square root of A times square root of B, square root of A times B. And 16 times 5 is 80. And root 80 is almost root 81. That's really close to 9, I bet you, but it's between 8 and 9. See, that's a much better approximation than somewhere between 8 and 12. See, this is much closer. And probably much closer to 9, right? So I'm gonna, just for kicks and giggles, I'm gonna enter 4 times square root of 5. And when I square this, I should get 80, right? 4 root 5 is square root of 80. Oh, but let's look at it as a decimal, 8.9. It's almost 9, right? And if I square, that is your 80. So that's important, actually, that you can get better approximations if you, instead of getting the squares out from under, you in fact do the opposite and you shove things back under. But it all has to take place with multiplication, division. Addition, subtraction, none of that will work. None of that. Okay, any questions so far? Are you sure? Let me see. Hmm. Okay. So this is gonna be the part where I think this algebra is better than the one with letters. This is more fun. And in a way, it's more easy. So let me just say that square root of 2 is like x. And by that, I mean it's unlike terms with the numbers or with square root of 3, except square root of 2 squares to 2. When we square root 2, we get back 2. When we square, and here is why this is going to be so much nicer. With higher and higher power of x, they are all unlike to each other. X and then x squared and x cubed, and x to the 4 and x to the 5. The higher degree you are, the more unlike terms you have. That's not what's going to happen with the radicals. They're lovely. All right. Oh, let's see higher and higher powers. So square root of 2 is square root of 2. X, I'm going to just do x squared, x cubed, x to the 4, x to the 5, x to the 6. Now, square root of 2 squared is
2.
2. And then you can always say, I'm not going to start from scratch. I'm just going to multiply the previous result by square root of 2. But we can start from scratch. Square root of 2 to the 3rd power. And then there are all kinds of ways to get there. You can say root 2 times root 2 times root 2, and this is 2 here. Or you can say, I'm just going to multiply the last one with square root of 2. Or you can say, well, root 2 times root 2 times root 2 is root 8. Oh, that's not going to help. Yeah, that's not going to help. Square root of 2 to the 4th power. Okay. Square root of 2 to the 4th power.
Would it be 4 square root 2?
No, it would be 4. And so there is something important that I want to point out here. So you can just multiply this by root 2, and then root 2 and root 2 together would give you a 2. But also you can just pair them up and say this is 2 and this is 2, right? But in general, if I say something like square root of 2 to the 18th power, I want you to remember this a to the n to the mth power equals a to the n times m. And if you're dealing with square root, then a 2. So you could take this apart, square root of 2 to the 18th. You can take it apart, that 18 as square root of 2 squared, and then further exponentiate it to the 9th power. And square root of 2 squared is 2. So we're talking about 2 to the 9th, which is 512 or something like that. Right? That would work here too. It's basically, you can take square root of 2 square and square again, right? For the 4th power. But either way, you're going to get 4. Square root of 2 to the 5th power, which is also square root of 32. No, I don't believe you. Really? Square root of 2 to the 5th power. I told you can multiply the previous one by root 2. What's wrong with that? if you start from scratch, root 2 times root 2 times root 2 times root 2. This is 2, this is 2. So you have 2 times 2, 4 times root 2. Square root of 2 to the 6th power. Come on, you don't want to do this until the end of class, right? I'll stop when you guys get it.
Six.
No, but that's forgivable. It's 8. But I know you thought the right thing. It's basically, you can multiply 4 root 2 by root 2. And then when you have 2 root times 2 root 2, when you have root 2 times itself, that's a 2. What about square root of 2 to the 7th power?
8 square root 2.
Exactly. And square root of 2 to the 8th power. It's 16. And now it's clear because I told you just grab the previous one. This is a mathematician's kind of laziness. Let's use what we had. But if you are given this from scratch, I would say square root of 2 to the 8th power. Think of 8 as 4 times 2. And then square root of 2 squared, further exponentiated to the 4th power, right? Because these square roots really like to be squared, because then you're back to solid ground numbers that you know. So we have 2 to the 4th power, which is indeed 16, right? Okay, square root of 2 to the 9th power.
$16 square root 2.
Yes. And square root of 2 to the 10th power is 32. I'm stopping here. But notice that if the exponent is even, we are back to nice numbers. That's not what x squared and x to the 4th and x to the 6th and x to the 8th does. And then the other, it's just there are two groups. You can take any combination of square root of 2 and all kinds of powers is gonna just boil down to something like square root of 2 plus 5. It's not gonna be long. See, these are the ones that are like terms with each other. There is just two groups, which means that you can have higher and higher end powers. Those things will not get longer. It's just always going to be nice numbers and a bunch of root 2, which is much nicer than longer and longer polynomials that you get. So in a way, this is nicer. I really like the algebra that is going on here. You will see. All right, let's pull this out. Okay, this is not new material. Chop. What do we get when we multiply this out? This is not even this course, previous course. Come on. All right, I don't have time for this. So f will give us 2x squared. O will give us plus 4x. I will give us minus x, and L will give us negative 2. O and I, as always, will combine, well, as long as you're organized. Okay, now for the fun part. And again, the analogy is not accidental. Okay, it's basically all I did, I replaced x with square root of 3. And now when we apply the FOIL, the first step is the same. We have 2 square root of 3 times square root of 3 coming out from f in FOIL, right? 2 root 3 times root 3, which is in the next line is going to turn 2 times 3, which is going to be 6. And eventually you can just jump to 6. If not, take your time. Plus, and O and I are identical, like before, instead of x, but plus 4 of them, minus 1 of them, plus 4 root 3, minus 1 root 3. And we combine like terms just the same way O and I combined before. and L is the same, but now O and I always combines, but right now F and L does too. F and L are like terms, right? It's always going to collapse down to two pieces. Nice numbers, yucky numbers. So what do we get? These two talk to each other as well, right? So we get 4 plus 3 root 3. That's it. This might not be a bad idea to check with the calculator. You should be able to handle these expressions in the calculator. Does this help? No, doesn't help at all, does it? Okay, so I'm gonna parenthesis open 2 times square root of 3. Now, whenever you enter square root, the calculator opens a parenthesis for you. You have to close that. Minus 1. Otherwise, you take the square root of 3 minus 1. That's not the intention, right? We just entered this. Times, parenthesis open again, square root of 3 plus 2. Okay, and it's 9.196. You can take down the decimal for comparison, 9.196. I also want to show you that your calculator can store up to 5 numbers. This STO is short for store. And if I enter, then it will offer me A, B, C, and D. A has something in it. It has 233 and change. And with the arrows, C is empty, D is empty, E is empty. But I'm just going to enter it into A. Oops. I'm just going to enter it into A. And it says, okay, the answer went into A. So then there is no pressure on you not to mess up stuff. And then we can, of course, enter 4 plus 3 times square root of 3. And it's the same stuff. But there is fun ways of checking in. So I took all this work to enter this, and now I want to prove that it is this. So I'm going to say, if we did everything right, these two are the same. So if I subtracted 4, now what I'm looking at is 3 root 3 or square root of 27, right? Or, well, okay, maybe it's a little too advanced to say this is square root of 27. It's 3 root 3. So then we can divide by 3. Now it should be root 3. So if I square this now, it's kind of fun. But you can take down the decimals and compare. Okay, any questions? So let's do 2x minus 3 squared, which is 2x minus 3 times 2x minus 3. And so we get 4x squared from F. O and I will both give us the same thing, minus 6x, and L will give us 9. And then O and I can be combined, F and L won't. And that's why polynomials are worse than these radicals. Now let's see 2 square root of 5 minus 3 squared. So again, it's analogous. It's just I swapped x for root 5. So it's 2 root 5 minus 3 times 2 root 5 minus 3. Hey, can you tell me just in one step, what is 2 root 5 times 2 root 5? What will we get out of F in FOIL? 2 root 5 times 2 root 5. What is that?
4 root 5.
Well, it's not root 5 anymore because 2 of them meet, right?
Is it
It's
just
4
4 then?
It's 20. It's 20 because 2 times 2 is 4, root 5 times root 5 is 5, and 4 times 5 is 20. Just go as fast as it's safe. We can say 2 root 5 squared, and that's 2 squared root 5 squared. That is your 4 times 5. See, 20. Then out of space. Okay, O and I is similar, really similar to with X. We have a -6 root 5 and another -6 root 5, which can be combined to -12 root 5. So we have -12 root 5, and then L is the same. -3 times -3 is +9. But as I was telling you, that now it's not just O and I that can be combined, but F and L as well, right? So we get that 2 square root of 5 minus 3 squared is 29 minus 12 root 5. Let me ask you a question. Is 2 root 5 minus 3 positive or negative? Tell it to me without the calculator.
Negative.
Why do you think that?
It's positive, I think.
Me too. So it's generously positive because you can just say, well, root 5 is more than 2, and then 2 times 3, we're above 6, 6 minus 3. But also if you shove these 2 back under the radical, that 2 becomes 4. So this is root 20, which is more than 4 actually, right? Is positive. Okay, then, so you understand that 3 squared equals 9 and square root of 9 equals 3 are related statements, right? So let me mess you up. 2 square root of 5 minus 3 squared equals to 29 minus 12 root 5, or square root of 29 minus 12 root 5 is 2 root 5 minus 3. I had to be able to go from here to here. It's not that hard because you see the root 5 and the 12. From that you can get the other number. So it's not that difficult, but you see, I'm just, and now you understand why I had to first make sure that this number is positive, because -3 squared is 9, but square root of 9 is not -3, it's 3, right? But if this number is positive, then if you square, you get that number, then that number's square root is 2 root 5 minus 3. How wacky that one is. Don't worry, you don't have to know that. You just have to be able to go from here to here. But as I said, it's not that difficult. Okay. Let's do x minus 2 to the 3rd power, and then we're going to do square root of 3 minus 2 to the 3rd power, which should be negative, right? Root 3 is less than root 4. This is a negative number raised to the 3rd power. This should be negative. I just want you to experience how much better the radicals are than just the letters. Okay, so let's do x minus 2 cubed first. X minus 2 times x minus 2 squared. I'll take this out. You remind me. Which is x minus 2 times, now x minus 2 squared is x squared, minus 2x minus 2x is minus 4x, minus 2 times minus 2 is plus 4. And now we go again. We're expecting 6 little products. One when we hit all 3 of these with x, and another one with -2. So we have x cubed minus 4x squared plus 4x minus 2x squared plus 8x minus 8. And then we combine like terms, x cubed minus 6x squared plus 12x minus 8. All right. Now I'm telling you that square root of 3 minus 2 to the third power will have two parts, a root 3 part and a number part. It's not going to get longer just because the numbers will get higher and higher, but it's not going to get longer. So square root of 3 minus 2 to the third power is square root of 3 minus 2 times square root of 3 minus 2 squared, which is square root of 3 minus 2 times. All right. Work out square root of 3 minus 2 squared. Work out and report back. What is square root of 3 minus 2 squared? Grab some paper, foil it. Now you're either done or you're just sitting there. Is there anyone who actually needs more time? Okay. So eventually you're going to be able to say square this, square that, and add. Squares to 3, squares to 4, that's 7, minus 2 times 2 times, minus 4 root 3. Until then, you can just FOIL. But did anyone actually do it and got 7 minus 4 root 3? 4 root 3 minus 2 squared? Now, square root of 3, you should learn to recognize square root of 2 and square root of 3. They're kind of famous. Square root of 2 is 1.414, I don't know more. And then square root of 3 is 1.73. So I'm going to do the following. I'm going to do parenthesis open, square root of 3. The square root parenthesis closed, minus 2 squared, minus 2 parenthesis closed squared. And I'm hoping that that should be 7 minus 4 root 3, right? These two should be the same, if I'm right. So if I added 4 times root 3 to this, I should get back that 7, right? So I'm going to add plus 4 times square root of 3. So, cute little. Again, you can punch in, take down the decimal, punch in, take down the decimal, and compare. It's just less fun. Okay. So just for your notes, square root of 3 minus 2 times square root of 3 minus 2. When we FOIL, we get square root of 3 squared, which is 3, minus 2 root 3 and minus 2 root 3 for O and I, which can be combined to minus 4 root 3. And then negative 2 times negative 2 is plus 4. And then we have 7 minus 4 root 3. But we are not done. That's just a square. So now, for square root of 3 minus 2 to the third power, we have square root of 3 minus 2 times. And now, see, I got this, but in these cases, that makes me feel weird. It's like x, so I like to have it up front. So I personally would swap it like minus 4 root 3 plus 7. So I know what to expect, that f is where x meets x, or otherwise, this one is a little, I don't know, I have to stop, slow down, and be careful, and I don't like having to do that. But that's up to you. That's just my bias, is not the material. All right, so f will give us, oh, what is f? What is square root of 3 times minus 4 times square root of 3? What is that?
Is that negative 12?
It is. 4 is waiting while root 3 and root 3 happily meet, and their product is 3, and 3 times 4 is 12. and go as slow or as fast as you feel safe. And then there is a +7 root 3 and a +8 root 3. But as I said, oh, this is why it's going to be negative, -14. Wow. So again, F and L and O and I, it's more even. It's like two, from the 4, it's going to be 2 pairs. -26, wow, plus 15 root 3. And now suppose you want to check out without a calculator whether it's positive or negative. You probably should jam this under the square root. And then if you don't have this multiplier, just a radical, you can put it between 2 consecutive integers. Just for kicks and giggles. 15 squared is 225. Remember when it's 225, 3 times -26 plus square root of 3 times 225. 6, 7, 5. Be careful, 3 times 225 is 675. I think 676 is a square. Wow, it's really small. So basically this squares to 676, this squares to 675. So they are really, really close to each other. Now I'm curious. So square root of, by the way, there is an operation called the floor. The floor is, imagine that you're on a number line and everyone falls into the nearest lower integer. So, and it looks like this. So the floor of 5 is 5. The floor of 10/3 is, well, 10/3 is 3 and change. It's 3. So what we're doing here is actually something that actually comes up. It's the floor function. When I say 9 and change. So 15 square root of 3, the floor of that, it's much better to come up in this form, 675. And that's 25, because 25 squared. Sorry. This is not as easy. Okay, there. 25 squared is 625. And 26 squared is 676. So this is going to be between 0 and -1. But I think it's going to be pretty close to 0. So I'm going to enter this and this. Let's say we're checking. Okay, I'm going to try to, just 2. All right, this is visible, right? So we're going to say square root of 3 minus 2, close parenthesis, to the 3rd power. See, it's a minus, not even 2%, minus 0.019. So if it was money, it's less than 2 pennies. It's not a lot. And then 15 times square root of 3 minus 26. There it is, same thing. Okay. And if we would raise stuff to the 4th power, the polynomials just get longer and longer. You would have x to the 4th, x cubed, x squared, x, and the number. Here, they always will be as short as 2 pieces. 1 piece for the radicals, 1 piece for the nice numbers. It's just that the numbers under the radical and not under the radical, these numbers are, the coefficients get bigger and bigger. But it's kind of fun. I think it's a much better game than with x. Any questions? All right. So let's do you know what we're doing is basically, this is sort of the last few letters of the alphabet that will give you literacy. Like, this is part of the language that people assume you're familiar, not fluent in. If you do any science, even if it's just loosely related to mathematics. So it's part of the language. There is one more thing that used to be in intermediate algebra, now it's in college algebra, and then that's it. So it's finishing touches of being able to handle any real number. It's pretty neat. Okay, so let's do square root of 2 minus 1 to the third power. And I kind of hope, let's do square root of 2 minus 1 squared first, and you tell me. And then when you're done, you're going to multiply it by square root of 2 minus 1 again for the third power. Chop, chop. Yes, I see one correct answer is in the chat box. Eventually, you're going to be able to just say this squares to 2, this squares to 1, that's f and l, that's 3. And then minus 1 times root 2, 1 times root 2 is 2 root 2. But, and that's just me, for the purposes of multiplying it any further, I will swap and have the yucky part play the role of x. But that's just me. So what is the first piece? What do we get when we multiply these two? Yes. In my chat box, secretly sent to me -4. See, there is a 2 waiting for the other 2 root 2s to meet. And then O will give us +3 root 2. And I will give us +2 of them. And then L is as usual. And then O and I as usual, and F and L, -7 plus 4 root 2. So this thing is not getting longer, just the numbers in the expression.
Why would it be 4 square root 2? Wouldn't it be
Oh,
5?
Yeah, thank you. Thank you. My professor told me when he found out that I was planning to become a math teacher, he started to teach me not just the math, but his sleazy little tricks. And he said, you know, whenever I suspect that I lose the audience, I make an error intentionally. And if no one reacts, I know I lost them some time ago. And I thought, oh, that's so smart. I'll do that too, but I make my own. So I never had to resort to intentionally make a mistake. But I'm glad you're here. You're still with it. And by the way, this is why it's a nice little exercise to check it with the calculator. I would have picked it up, probably, hopefully. Any questions? You know, the difference of squares theorem has to do with multiplying conjugates. That still applies, and it's lovely, very useful. If you have something like square root of 5 minus 2, and you want to get rid of the radical, squaring it's not going to help. In fact, squaring it will make it worse. Because if you square it, square root of 5 minus 2 squared is going to be this squares to 5, this to 4, 9 minus 4. Now that is 4 of them. There's more of them now, right? But what will cure radicals is the conjugate. What do we get when we multiply square root of 5 minus 2 and square root of 5 plus 2? What do we get? Yes, I got the correct answer in the chat box secretly. Yeah, when I cancel, F will give you 5, L will give you -4, and so it's 1. Now you can fold the whole thing or see way down the road with O and I, or it's really up to you how much detail you want to include. But check this out. if two numbers multiply to 1, they're reciprocals. So square root of 5 minus 2 and square root of 5 plus 2 are conjugates and reciprocals. And take this equation here and divide both sides by square root of 5 minus 2. That's going to look weird, but it says basically square root of 5 plus 2 equals 1 divided by square root of 5 minus 2. Right? I just rearranged this thing by, forget the middle, square root of 5 minus 2 times square root of 5 plus 2 is 1, and divide both sides by this. And you get that. Well, if we have this, there should be a way to get to this form, right? This is much simpler. And that takes us to this, well, yeah, let's do that. So there is this thing about rationalizing denominators. And that was especially important before the time of calculators. So rationalize. Let's say we have 3 divided by square root of 5. So rationalize, or rationalize the denominator means the following. This number is irrational. There's nothing we can do to change that. Where we have a choice is which part of the fraction do we want to carry the irrational stuff. And there is an easy way to transfer the yucky stuff from the denominator to the numerator. And this is no longer so essential, but it's still useful. You should not want to bring stuff to the common denominator unless they're all that nasty, because then it's just asking for trouble. So we're going to multiply this fraction by 1, where 1 is a fraction carefully selected to fix the denominator. In this case, just root 5 over root 5 will do the trick. The numerator is 3 root 5, and the denominator is 5. Or something as simple as 1 over square root of 2. When we multiply it by square root of 2 over square root of 2, we get square root of 2 over 2. And we enter the same conversation where officially this is always bad, this is always good. That's not true. This is much easier to square than this. This will squares to 2 over 4, right? This is just squares to 1 over 2. In fact, in many ways, this is simpler. But if there are other fractions inside, even just near it, rationalize the denominator. Otherwise, it's terrible. You do not want to have a lot of radicals in the denominator. But what if we have something like, this? Now squaring it won't fix. So you use the conjugate. You multiply upstairs and downstairs by the conjugate of the radical thing. Those conjugates will make those radicals go away. So we're going to multiply both upstairs and downstairs by square root of 7 plus 1. And then if the problem is from me, don't even worry about the top, just indicate it. Because if the problem comes from me, there is going to be simplification. You would have to refactor it. What do we get in the denominator? Go as slow or as fast as you want, just get there. What is root 7 plus 1 times root 7 minus 1? 6. And you see there is some cancellation. So finally, square root of 7 plus 1 over 2 is the final answer, which is indeed much, much friendlier than this hideous thing here, right? Yeah. Any questions? This is a funny one. You know, the theory is simple enough, but there are situations, little algebraic banana peels, and I just put them all those exams. There is a banana peel in this problem. Is there? Maybe not. Oh, well, just change one sign. So you can either go -3 minus root 10 or 3 plus root 10. I would never add another negative sign. So I would go 3 plus root 10. It doesn't matter. It doesn't matter which one. They're gonna be opposites, right? If you have a plus b, well, let's say you have a minus b. So the comment in the conjugate in the chat box is that, oh, I got kind of lost on which conjugate to use. So this one has two conjugates. You can do a plus b or minus a minus b, and they are just opposites of each other. So there is just one minus sign that's going to cancel out anyway, because you're going to insert it in top and bottom anyway. So it doesn't matter. Just go with the one that you like more. I would go with 3 plus root 10. Although actually, in this case, -3 minus root 10 might be a smarter choice. What do we get in the denominator? 3 plus root 10 times 3 minus root 10. Chop, chop. -1. And so let me show you what error. I set people up for this error. Let me show you what error I often see. Because this is not acceptable for two reasons, the 1 and the minus. And what's wrong with this one here? Come on, to get rid of that -1 in the denominator, we multiply both upstairs and the whole upstairs and downstairs by -1. So you get -3 minus root 10, not +3 minus root 10. I very often see that weird error that they leave the minus here, but and then the other thing, this is like so obviously so badly positive. This doesn't appear to be so negative. This is so negative. And then, you know, this is negative because 10 is bigger than 9, right? So it's a good skill to be able to sort of approximate and compare these radicals to regular numbers, because it will inform you on yeah, this as a student would freak me out, way too negative compared to this. And then you look closer, and it is negative for a reason. And 9 and 10 are close to each other. So the denominator is a tiny number. The reciprocal of tiny numbers is usually big numbers, right? It's a balancing act. You have to multiply to 1. So tiny times bigger will give you 1/10 times 10, or 10 times 1/10. Okay. And that's how you do that with that 1/√5 minus 2. We just multiply upstairs and downstairs. Now this is positive. That's why I thought maybe -3 minus root 10 would have made that problem go away, but I'm not sure it's worth having so many minus in the main computation. See, the denominator is 5 minus 4, that's 1. And the numerator is √5 plus 2. I don't know if you ever computed with decimals on paper, but let me assure you, if you have a book with values, like you have a book which up to 6 decimals, you can read what square root of 2 is, square root of 3, square root of 5, square root. So this one, you just look up in the book, square root of 2, and you use the paper to divide by 2. It would take an afternoon to divide by a long decimal, right? So 1 divided by this expressed up to 6, 7 decimal, that is just much longer than this. So rationalizing the denominator was more important at the time when there were no calculators, but it's still a good practice. It's still quite necessary in certain situations. Any questions? For those of you still conscious in front of the computer? All right. So whenever you see exact value, that means you cannot use decimals. You're stuck with the radicals. So find the exact value of -x² plus 3x plus 4 if x is 2√3 minus 1. All right, now It's not a difficult problem. It's more like 4 easy problems piled up on the top of each other. So my recommendation is maybe you should work out x squared separately, because if it takes more than one step, you should not have to drag along the rest. And yeah, you might need to. So let's work out separately x squared before we start with the main thing. X squared is 2 root 3 minus 1 times 2 root 3 minus 1, and off we go, FOIL. What does f in FOIL give us? What is 2 root 3 times 2 root 3? 2 root 3 times 2 root 3. Two times 2. Oh, wait, you're right. No, 4 times 3. Right? We just lost one. We just lost someone. So I see 6 in the chat box, but I think it's 12. Yeah. 4 times 3. This squares to 4, this squares to 3. So we have 12, and then O and I are the same in case of a complete square. Minus 2 root 3, minus 2 root 3, which is going to be minus 4 root 3, and then plus 1, and 12 and 1. So it's 13 minus 4 root 3. I recommend you do this elsewhere, and you don't have to drag along the rest of the computation while you're working on that. Negative 1 times 13 minus 4 root 3 plus 3 times 2 root 3 minus 1 plus 4, and the rest is hopefully pretty easy. We get negative 13 plus 4 root 3 plus 6 root 3 minus 3 plus 4. Distributive law. So we have 10 times root 3 minus 3 plus 4 is plus 1 minus 12. And if you have time and in the mood, you should check with the calculator. They'll work out with your fingers. Any questions? Okay, all right. So then I'll stop here for this topic, but this one was just really, really important. Tuesday's material and this one, really important. If I didn't have to review, I would start with this. But obviously, most of you could probably benefit from all that review.